All right, so as promised, we're going to go ahead and talk a little bit about Newton's second law and polar coordinates. The last about a week or so, we did Newton's second law and Cartesian coordinates. We talked about it, and then we did, a series of problems on it. Now we're going to do the same thing. We're going to talk about Newton's second law and polar coordinates, and then we're going to work through some of those problems. And then after that, we'll see what we'll do. Maybe we'll do a little more problems in chapter 1, or we might just go ahead to chapter 2 and talk about air resistance and drag force. But for right now, we do need to talk about Newton's second law and polar coordinates. So everything I've drawn now should be pretty okay. One thing to note, I'm using the angle phi, that symbol to represent the angle between our vector, which we'll call this R, and the horizontal. That's what they use in the book. Theta, it's the same thing, just you would change your symbol. What I hope you know is that the x-coordinate is our cosine phi, y is our sine phi. That can be given just from right triangle trig. This is a right triangle. The magnitude, r squared, is equal to x squared plus y squared by Pythagorean theorem. And the angle is tan inverse of y over x. So hopefully you guys are okay with that. The next bit might be a little different, and that's okay. Let me actually move this over a little bit so I have room. That's fine. I guess it can be read. And that's going to be the unit vector, r hat. Now, the way I want you to imagine this is imagine theta is constant. It's where it is. R hat is going to be the unit vector pointing in the direction where r is increasing. So if theta is staying the same, then r is just going to point continuously in that field at a unit's length. Now, r can change. Maybe, r shoots all the way over here. Maybe it's just, maybe it's just down here. It doesn't really matter. But what is important is that our r hat vector is pointing in the direction, it's a unit vector pointing in the direction of increasing r. And then perpendicular to that, we're going to have phi hat. Now imagine r is staying constant. It's not changing. But I can take this blue vector and I can swing it all around. Theta hat is perpendicular to r hat, and it points in direction where theta would increase. So this is actually, they're perpendicular to each other. So hopefully that makes sense, just those unit vectors. We needed to talk about them for a second. And now let's go ahead and bring up some more stuff, some stuff we got to know. First off, r is equal to x hat plus y hat. And because we know what x is and because we know what y is from the green up here, we can just say that this is going to be r cosine of phi x hat plus r sine of phi y hat, which all we're doing is replacing x and y. Okay, and the reason why I did this is because it's important to know for r hat, because r hat is our r vector divided by the magnitude of r. That's how you get a unit vector. You take a vector and you divide it by the magnitude. You'll always get the unit vector. Hopefully that's also not something incredibly new to you. Okay, well, r vector, we just said, was r cosine of phi x hat plus r sine of phi y hat. And the magnitude we're just calling r. So the r's all drop. And finally, we get r hat is equal to cosine of phi x hat plus sine of phi y hat. This comes up a lot in what we're doing, so I'm going to box that. And I think it makes sense how we got there. It's not totally out of nowhere. Now you might ask yourself, okay, that's r hat. What about phi hat? Well, I'm going to draw phi hat. So I'm going to draw the magnitude of phi hat right here. And then these are the components. This is phi hat in the y direction. This is phi hat in the x direction. Now, I guess the best way would be, imagine if you moved phi hat right here. This is essentially the triangle I just drew. Well, this angle right here is going to be 90 degrees minus phi. So then that means this angle is phi. Okay? So hopefully that makes the geometry make sense. That's phi. All right. Then phi in the x direction is going to be the magnitude of phi times sine of phi. And this is to the left, so there's a negative. And we're going to get, in the y component of phi, the magnitude of phi times cosine of phi. But keep in mind, phi is a unit vector, so the magnitude of a unit vector is just 1. So if we want to describe phi hat, I'm supposed to be saying phi hat. If I'm not, then that's what I mean. So phi hat is equal to your x component minus sine of phi hat. This is the x component plus cosine of phi y hat. So this is how we're going to describe phi hat. Another important one that's worth boxing. Okay, so now that we have all that, let's do this. Let's look at our position vector, r. We want to take, let's actually review really quick. We know force, the sum of all forces, is equal to mass times acceleration. And I'm going to use the subset I. That could be the I could be an x, it could be a y, it could be different sets within our coordinate. So what we're looking for here is the acceleration. So the acceleration is the second derivative of position, right? We know another way to think of Newton's second law, we talked about this before, is mass times the second time derivative of position. So what we have is our first position, that's r hat, or I'm not r hat, that's just vector r, I'm sorry, which we said was r cosine of phi x hat plus r sine of phi y hat. So we want to find our acceleration, how we could write acceleration in polar coordinates. So you might guess to do that, we need to take two derivatives. And the first derivative will get us our angular velocity. Okay, that's going to be d by dt of r cosine of phi x hat plus r sine of phi y hat. Now this might look really quick and easy, but here's the thing you want to know. R and phi can change with time. In other words, we're not thinking of the radius or phi as just staying put. They can change. So because of that, what we're dealing with is two separate variables that change with time. So what we have to do here is, first off, this is a product. Both of these are product rules, right? Hopefully you recognize that product rule. So let's do the product rule. If you're not familiar with the product rule, I talked about it in an earlier lecture worth checking out. Okay, so let's go ahead and take the derivative. Let's start with just the first part. The derivative of our first function will be just r dot. That means it's the time derivative. Times cosine of phi plus or minus r sine of phi. But when I take the derivative of cosine of phi, I also have to remember that there's a chain rule there. And when we do that, what am I going to be left with? The derivative of the inside. What's the derivative of phi? Phi dot. The time derivative, at least. So the big thing is to know, okay, r changes, but so does phi. So I can't just take the derivative of cosine of phi and call it sine of phi. I have to multiply by the derivative of the inside. So that's our x component. Plus, basically the same thing with the next part, r dot sine of theta, plus r, or not theta, cosine of phi, and then same thing here, we need a phi dot, and then this is our y hat. Okay, so this isn't too bad. Let's see what we can do here in terms of combining and expanding in certain ways. So dr dt. So what I'm going to do is every term that has an r dot, I'm going to factor that out. So right here, there's a cosine of phi. And then over here, x hat. And then over there, there is a sine of phi. So plus sine of phi. And then there's the y hat. Okay. So far, so good. Plus, now the ones that just have r in them, they also have a phi dot. So that would be this term and this term. And if I factor that out, I'm going to be left with a minus sine of phi from the one on the left hand side, plus cosine of phi from the right hand side. Oops, there's an x hat there. X hat plus cosine of phi y hat. Now here's the thing. This is really r hat. If we look up, cosine phi x plus sine phi, yep. And then this guy here is phi hat. Okay. So we can say dr by dt is just equal to r dot, r hat, plus r phi dot, phi hat. So, okay, there's our first derivative, but we're interested in acceleration. Let's not forget about that. And acceleration is the second time derivative of position. So we found what would be the velocity, which you have to do to get to acceleration. But now we have to take another time derivative. So let's do it. D by dt of r dot, let's draw that a little better, of r dot, r hat, plus r phi dot, phi hat. Okay, so let's break this up a little bit. We can think of this as just being two separate derivatives, d by dt of r dot, r hat, plus d by dt, r times phi dot times phi hat. Okay, well, let's see what we can do here, and hopefully we can finish this derivative off, again, we're going to have to utilize the product rule. So derivative of the first, r double dot r hat, plus r dot. Derivative of the second is just dr r hat, sorry, dr hat dt. Okay, so f prime of g plus fg prime. Plus, now this is kind of like a double product rule. So what do we have? We'll have r dot, phi dot, phi hat. So what we did is we're treating this like this is, say, f, and this like it's g. F prime of g plus fg prime. Okay, so we have r dot, phi hat, plus r, phi double dot, phi hat, plus r, phi dot, d phi hat over dt. Okay, so the first one's pretty easy. The second one's a little difficult. So what we have to do is, number one, we have to find f prime. Well, f prime's its own product rule. So we would say derivative of the first is this, plus, then we would say r phi double dot. And then keep in mind, when we do that, we're actually going to be adding in the hat there, because when you're taking the derivative of it, there's also, you're multiplying it by your g constant. It's f prime times g, and our g is phi hat, so they're all going to get a phi hat. Make sure you can work through that. If not, review the product rule. I can do more examples on it if that's necessary. Okay, so let's go through this bit. We have r dot dot, r hat, plus r dot times the derivative with respect to time of our r function, or r hat, I should say, which r hat we've already found, right? It's the one in orange. So we can just plug that in right here, and that's cosine of phi x hat plus sine of phi y hat plus r dot phi hat plus r phi double dot phi hat plus r phi dot times the derivative with respect to time of phi hat, but that's also written down. That's the one in red. So that's going to be minus sine of phi x hat plus cosine of phi y hat. All right, so r double dot r hat plus r dot times, all right, we're gonna have to take a couple derivatives here. That's okay. So let's see, the derivative of cosine of phi is going to be minus sine of phi times phi dot, that's in the x direction, plus cosine of phi dot y hat. So remember, we're doing the chain rule again, plus r dot phi hat plus r phi double dot times phi hat plus r phi dot times. All right, so what I'm going to do actually is factor out a negative. I'm going to go a little quick. Hopefully you guys are okay with the product rule. If not, again, check it out. So we're left with cosine of phi dot x hat plus sine of phi dot y hat. Again, the negatives factored out. So while the derivative would get me a negative here, and this would give me a negative, I factored those out to make them both positive. Okay, well, the key here is to see that this bit is phi hat. That's just phi hat. And this bit is just r hat. So this simplifies to r double dot r hat plus r dot phi hat plus r dot phi dot. Let me draw that a little better. Phi dot phi hat plus r phi double dot phi hat and then over here minus r phi dot squared. If I factor out the phi dot, r hat. Let me just check my notes to make sure we're all good. R dot r hat plus r dot phi. Is there a phi hat that's supposed to be here? Ah, there is. I need to factor out the phi dot. I skipped that part. Sorry about that. I was going to say I thought there was supposed to be a 2r at one point. So I'm just going to factor that out. And then what I'll do is I'll leave them in there, but just know you factor that out. I did it over here at the end. Okay, we're all good now. Okay, so now that we do that, let's go for the kill. We get close to the kill here. So real quick, let's see if we have any like terms. We do. So this is r dot dot r hat plus 2 r dot phi hat plus r phi double dot phi hat minus r phi dot squared r hat. So finally, we can say our acceleration is equal to, well, for the r components, we have, if I factor out r hat, so here and here, I get r dot minus r phi dot squared r hat. And then for the last two, plus r phi double dot plus 2r phi hat. And there you go. We did it. This is the acceleration. So the way we will think of this is the sum of all forces. Let's say we want to look in the r direction is equal to mass times acceleration times r hat, which is equal to mass times our acceleration is r double dot minus r phi dot squared. As for the r hat, well, r hat dotted with r hat is just 1 because any vector dotted with itself is just 1. And then r hat dotted with phi hat is 0 because they're perpendicular. Okay? Remember, the dot product is really telling us how parallel two vectors are. So if you have the exact same vector, they're going to be 100% parallel. If you have perpendicular vectors, they're going to be absolutely not perpendicular or parallel. So that takes care of the unit vectors that we see there. And we can do the same exact thing in our phi direction. And the unit vectors work out the same way. So very nicely, mass times r times phi double dot plus 2r phi. And these are Newton's second law in polar coordinates. Now, let's talk a little bit about, well, first off, I think it's worth explaining why this is necessary. This seems like it's a lot more complicated than what we did in Cartesian coordinates. And you might say, well, what's the point? Well, okay, fair enough. With the problems we've seen, if you're dealing with like a ramp, let's say, and you have a block on a ramp, it might make sense to use Cartesian coordinates to solve this, because you can just line it right up to the axis here. But if you're dealing with other problems, maybe like a pendulum, or they do an example in the book of a skateboard going up a little half ramp. If you have this little rock on a string and you're swirling it around, I've seen that one before. When you're dealing with problems like that have this sort of circular symmetry, it's very difficult to do Newton's second law in Cartesian coordinates. This actually becomes easier to do in polar, and they're a nightmare in Cartesian. So that's why we do these, and they're important to know. But let's talk a little bit about notation here. What does this mean? Well, obviously we're looking at the force in, say, the r direction. And what that means is that's the force that's pointing in the direction of your radius. So if you're here, your radius is going to be over here. So for example, your normal force would be pointing towards your radius. You obviously would have a force due to gravity, and part of that would be in the direction of your center, your radius. This force is talking about the ones that are they're pointing in that direction. They're swinging in that direction, which in this case would be our x-coordinate. That force is pointing in the direction that phi is changing. So that's kind of what we're meaning by the forces there, which I think could get kind of confusing. So, for example, here, if we looked at this one, the force pointing in our radial direction would be tension, right? Because the tension force would be, pointing over on this line, and maybe air resistance would be along our angle, because the force is moving in such a way that it's pointing in the direction where phi would increase. Hopefully that bit makes sense on why we would pick that. We derived the acceleration, which really took the most amount of time. And hopefully starting tomorrow, we'll go through some problems. Like I said, the book for John A. Taylor's Classical Mechanics, they go through an example with a skateboarder. I might go through that, I might not, just because they've already worked through the solution, so I don't know if it's necessary, but some of you might not have the book, so that's your only real way of seeing it, so I'll think about it. We'll see what we'll do, but